Short of getting a hacksaw and, carving out the back of this thing, I have tried everything else.
You don't want to destroy it, obviously. You want to have a non-destructive way to open the safe. This is my brother-in-law, Levi. Hey Levi, how's it going? So you said that you have a problem that you might need my help with? A couple of years ago, he bought a safe to store his valuables. He wrote the combination on a piece of paper and locked it inside before going on a long vacation abroad.
In a moment of genius, I said, to protect this gun safe, and because we were gonna have some folks here at the home, I'm gonna put the code inside of the gun safe, because I obviously would never have forgotten this code, right? Turns out after 2 weeks abroad and having fun and the time of our lives, I came back and immediately looked at this gun safe and I said, I have no idea what the code is anymore.
How many numbers are there on the dial? Is it like 0 through 99?
Yep, 0 through 99.
And then there are how many numbers in the combination?
It's 3 numbers in the combination.
3 numbers. So that would be so it'd be 100 times 100 times 100
times 100.
So that's like a million combinations. So yeah, so there's no way you're gonna brute force a million combinations. All right, so what do you need my help with? What were you thinking?
So I would love if you have like some type of auto dialer that has like a crank arm to, try a combination, crank it, try another combination and crank it. So then that way, hopefully we can get to a resolution. That would be wonderful.
I think this is a really cool problem. I think it like tickles all the right parts of my brain. I'm not promising that I can open your safe or that I'll do it in like any reasonable way, but like I just think it would be a fun project to try to open up a safe that you've tried all the other avenues and haven't been successful. And this would just be like kind of a Hail Mary to like try to one last ditch effort to try to get this thing open using like engineering. I think that's awesome. I'm totally on board. I'd love to help.
Awesome.
Cool, man.
Thank you
All right,
so much,
thanks,
man.
Levi.
And
I'll talk to you soon.
you, man.
All right,
Okay.
thanks.
See you
Bye.
later. Bye.
I'm not a locksmith, nor do I have any burglar skills, but I am good at engineering and problem solving and building things, so I think I'm gonna try to build a robot that can crack the combination to Levi's safe. After my phone call with Levi, I did some research and I found a video by the lockpicking lawyer. He demonstrated one of these auto-dialing devices on his channel, and I really liked the simple design, so I'm going to use this as the basis for my design. I gotta come up with a plan on how to build this thing. So if I have a safe door that looks something like this, and there is like a dial in the center here, and it has kind of a knob that I can grab onto, and then here's the little number indicators. It kind of looks like a donut, but you get what I'm saying, right? So I need to be able to spin this dial in such a way that I can test all of the different combinations. The way I'm envisioning this is walking up to the door and attaching this device magnetically and then hitting a button and then it starts going. I definitely don't want to have to drill any holes or like attachment points to the door of the safe, so that's what I'm going to try to shoot for. To give you a better idea of what I'm thinking about, let's go into the neighborhood of make-believe. As you can see here in my 3D model, I need to design something to put on the end of the motor shaft so that it can grab onto a dial. I could design some sort of coupler that would grab onto the specific dial that my brother-in-law has, but I want to be able to use this device on different types of safes that may have different types of dials. So I'm going to design some sort of coupler that is adjustable. I want to be able to adjust it and attach it to different sizes and diameters of dials. So what I think I'm going to do is use a chuck like this that has adjustable jaws that can kind of close down on different diameter dials. Obviously I need a way to attach this to the door of the safe, so I'm going to use a couple of metal plates that are connected together using some aluminum tube. But before I do any of that, I need to choose a motor that's going to be the muscle for this project. And of course, every motor needs to have a motor driver to tell it what to do. I also need to choose which microcontroller I'm going to use for this project. The microcontroller is going to have all of the code in it that tells the motor what to do. So I went ahead and I ordered a whole bunch of parts from DigiKey, so I need to go over to the electronics bench and start digging into this box. I gotta figure out how to turn this dial, obviously, so I'm gonna use some sort of motor. Now I've got a few options here. I could use like a servo motor, but I'd have to make sure that it's like continuously rotational servo motor. or I could use like a regular DC or brushless DC motor, but I'd have to use like an encoder on that so I could track my position. So what I ended up doing is actually getting a stepper motor, because these are very high torque and they also can count how many steps they've taken and keep track of their position. The cool thing about the one I got is that it actually has a trinamic motor controller already attached on the back of the motor, so I don't have to have an external motor controller. I can actually just mount this right on top of my device, and it's really compact. So this is what I'm going to use. I just ran into a bit of a problem here. When I ordered this, I noticed that it had what looks like a JST PH connector on here, but I'm going to insert a JST PH connector, and guess what? It doesn't fit. I would prefer to find the right mating connector, but I'm just not seeing that. You know what? I also have the mating part to that connector, so maybe, if it's possible, maybe I could like open this up and replace the connector on there with the one that I know I have the mate for. I really don't want to have to do that. Like, this is an expensive motor controller and I don't want to mess anything up by taking a connector off there. But I really can't think of another way to do this that would work really reliably. And I know for a fact that I have these two mating connectors, and one of them will fit on there because it's the right 2mm pitch. So I think that's what I'm gonna do. I'm gonna take off this cover here and try to desolder the connector on there and replace it with the one I have. This may not work. I'm looking closely at that, and there's tons of little components that are right next to the connector, and this one I'm trying to replace it with is actually quite a bit bigger. Well, at least it's wider on one of those dimensions, and I'm worried about it running into the components next to that connector. I went ahead and I pulled the PCB out of the enclosure. In order to get this huge piece off, I have to heat up all 9 of these solder joints simultaneously if this thing is going to come off. If I have 7 out of the 9 or 8 out of the 9, it'll still hold on and I won't be able to get it out. But if I do that, I run the risk of heating up some of the other solder joints and losing some of these other components. So to get around this, what I've done in the past is actually stick my tweezers or like pliers underneath this plastic housing part and actually just pry it up and then remove it completely from the board. With the connector totally removed from the board, that just leaves the 9 contact pins individually soldered on the board. So then I can just go through with my iron and heat up one at a time and pull those pin contacts out. I think the name of the game here is slow and steady. I don't want to damage anything here. So now all I have to do is just heat each of these little pins individually up with the soldering iron and they'll fall right out. There still is one last little problem. The cutout is still too small to fit the mating connector, but I think I can fix that by taking a file to it and opening it up a little bit. Now that I've swapped out that connector, I'm able to talk to the trinamic motor controller using my computer. This motor controller has a whole bunch of parameters that I can adjust and set using the IDE on the computer. One of the main features I was looking for when selecting a motor controller was one that could detect a motor stall. Once my device finds the right combination, it's going to try to open the safe and it will run into a hard stop. This is going to stall the motor. If I don't have proper motor stall detection, the motor will lose steps and I will lose my position, so I won't know where the motor is. or worse, I could do some damage. So I wanted to select one that had motor stall detection. So I chose this one in particular because it has motor stall detection. The problem I'm running into is that I cannot get it to work. I have read through all of the documentation and I have set every parameter the way it's supposed to be, but I still can't get this motor to stop spinning when a stall is detected. This whole project hinges on the ability to do this. If I can't get the motor to stop spinning once it's figured out the combination, there's no point in doing this. So I gotta figure this out. I've tried everything that I know how to do, and so I actually reached out to their tech support, and it turns out that this particular model does not actually stop the motor from spinning when a stall is detected. I need to actively be monitoring that stall detection and then stop the motor myself with the code that I write on the microcontroller. So that's what I need to do now. I need to connect my microcontroller to this motor controller and monitor that stall value, and when it gets to 0, I need to stop sending commands that will spin the motor. I need to choose a microcontroller to control the stepper motor for this project. I also want the microcontroller to have Wi-Fi, so I settled on the Feather Huzzah ESP8266. The stepper motor runs at 24 volts while the microcontroller runs at 5 volts, so I had to install a buck converter to drop the 24 volts down to 5. This stepper motor is controlled using step and direction signals, so it's super easy and simple to control. There's also a UART interface for configuring the motor controller, so I need to connect the RX and TX signals of the motor controller to the RX and TX signals of the microcontroller. So I've got these two wires that are the RX and TX lines going between the microcontroller and the motor controller, and now I'm going to plug in the Feather Huzzah board into this doubler board. I've got the motor here and it has that motor controller on the back and it's connected to the Wi-Fi microcontroller here. I've written some code on the Wi-Fi microcontroller so that when I plug it in and power it up, it will start spinning the shaft at a constant speed. The IDE shows that the load value is hovering around 210 when there is no load on it. But watch that number as I apply pressure using my hand. That number starts to go down, and if I apply enough pressure, I can get that number to go all the way down to about 0. And when it gets to 0, the motor starts to stall and skip steps. From my understanding, I need to tune all of the parameters so that that load value goes down to 0 just before the motor will skip steps. That way I'm detecting that stall and I'll stop sending motor commands before I actually lose steps in the stepper motor. My challenge now is that I'm able to connect to the motor controller using their IDE, but I need to be able to talk to this thing using my microcontroller, and the code that I write needs to closely monitor that load value, and when it gets to 0, I need to stop sending motor commands. There are so many things that could go wrong when building a project like this, but once I'm confident that my robot can crack the combination to Levi safe, I'm going to live stream the whole process so you can see firsthand whether it succeeds triumphantly or fails miserably. That was a lot of work. I've been working on this part of the project for like well over a week now, trying to read the load value on the motor to detect a stall. And I have run into so many problems, and it doesn't always come across in videos like this, like how much time I spend banging my head against the wall, trying to figure something out. And oftentimes things keep going wrong and I have to like stop working on the first problem to fix the second problem. Anyway, I have been working on this and I think I've got it working now reasonably well. I'm able to read from the motor controller the load value so it can tell me when the motor is about to stall, and my code is reading that value and it detects that and it will stop sending motor commands and halt the motor before the motor stalls. Now there's some fine tuning in the process here, and it all depends on like the speed of the motor and like kind of the load that's going to be on it. All of that is going to dictate the value that I'm looking for. So it's kind of hard to tune this because it's not in situ. I'm kind of just applying pressure with my hand and I can get the motor to stop, but I may have to do some more fine tuning and tweaking of the code to get it to work reliably once it's on the safe. But I'm moving ahead now, which is the important part. I've got this thing figured out. I've got the motor spinning and I can detect a stall and I can grab the motor and it'll stop. So let me show you what that looks like. This setup looks crazy because I have a whole bunch of wires coming into it from this digital logic analyzer. This has really been the unsung hero of this whole troubleshooting process. I know a lot of times when you're writing code, like for Arduino, you'll use print statements to kind of figure things out, but those don't always give you a lot of information. You can gather a lot more information by looking at the electrical signals, and having a tool like the digital logic analyzer really makes that so much easier because I can see exactly what signals are doing and when things are failing, and I can adjust my code that way. And I think it's much better than using print statements. So that being said, here's what I've got working so far. This might be a little underwhelming for you, but just keep in mind that this is like a week's worth of work. So I've got the code going. So if I reset it, this is gonna start spinning, and it's just kind of spinning back and forth. So if I hit reset, it boots up, and this should start spinning back and forth. And on the display, I have the load value, and it's hovering around 200 like it was earlier when I showed you. And if I put pressure on that, I can get that number to go down. And I have a little threshold, and once it gets below that threshold, it should stop the motor. So it was able to detect that stall and stop the motor. Now that I figured out this piece of the puzzle, I can confidently move forward with the rest of the project. I was a little worried about not being able to detect a stall because it's such a critical part of figuring this all out. So I'm glad that I've got this part working, and now I can move on to attaching this motor to the dial of the safe. And if you remember the model from earlier, I've designed a little adjustable chuck that is able to grab onto the dial. So let me go ahead and assemble that now. Here are all the parts that I need to build the adjustable chuck to grab onto the dial of the safe. This is a 1/4 inch shaft on the motor, so I've got a little coupler here that slides on. Then I have this 1/4 inch stud that is smooth on one side and threaded on the other. I've got a nut threaded on there that I'm going to use as a jam nut for this piece. So I'm going to thread on my 3D printed body of the adjustable chuck, and that will ensure that this doesn't come loose over time. This is that lead screw I was talking about earlier. So it has a right-hand thread on one side and a left-hand thread on the other side. Put the two jaws on there and turn this thing, they will either move together or move apart. It's always hard coming up with names like for mechanical parts because I'm not a mechanical engineer. I don't know what things are called, but I'm calling this the hub of the adjustable chuck. So there's 2 holes in it that go all the way through, and then there's a little spot for a set screw. So this main lead screw goes in the bottom hole here, but I don't want this sliding around back and forth. So I've got a couple of retaining clips to slide on here, but I don't have a little slot on the threaded rod to do that. So I'm gonna need to cut in little slots for these retaining clips to slide into. Once I get that done, I can slide in this guide rod that goes in the top here, and that will help guide the jaws of the chuck and keep everything aligned. I couldn't find a 4-inch length for this guide rod, so I'm gonna have to cut that down as well. So let me go take care of that real quick. I'm designing this whole device to open my brother-in-law Levi's safe, but he lives like 30 minutes away, and I don't want to have to drive to his house every time I want to test something. So I actually bought a really cheap safe to use for testing purposes. This is like one of the cheapest models you can get. It's actually not very secure. If you want to check out a really interesting video, the lockpicking lawyer took this exact same safe, and with a circular saw and a regular blade, he was able to cut through the thin sheet metal and the fireproof material in like under a minute. It was pretty amazing and really kind of opened my eyes to like how easy it is to get into something like this. I'm just gonna hold the motor by hand and attach it onto the dial here. And then when I hit reset, hopefully it starts to spin this dial. That is awesome. The reason it's so noisy is not my motor, it's actually this cheap dial. It's got so much internal resistance, it has that loud crackling noise. Watch, if I pull it off, it'll be really quiet. It's like almost silent once I pull it off. That's the dial that's making all that noise. Because this is a safe that I bought, I actually know the combination to it. So my next step is going to be hard coding the combination into the motor. Then I can have the motor input the dial combination and I'll unlock the safe. To make it easier to see what's going on, I've actually removed the inside door panel so that we can see the discs moving and we can see the gates all align up so that the handle can open up. I programmed in there 3 different speeds, and so this is running at the slowest speed just to test it. Obviously, once it works, I will show you what it looks like at the fastest speed. So that was the first number. It's going to the second number. And now it's going to the third number. You can see all of the gates have lined up, and now I can open up that latch and open up the door. Isn't that awesome? I went ahead and I did test it on the medium and fast speeds, and it lined all of the gates up properly, except that they were all rotated in the wrong spot, so I couldn't open the latch. I'm not sure what the problem is. My guess is that I'm actually rotating my hand as the motor spins, and that's kind of introducing some extra error in there. In addition to building a frame, I'm gonna have to develop a whole bunch of code for this project, and that's all gonna be in part 2 of this video, which is probably gonna come out in a couple of weeks. So make sure you're subscribed to this channel so you don't miss it. I've got some exciting news to share with you. I've been working really hard on building an online workshop that I'm calling Byte Sized Bootcamp. The first one is gonna be on January 19th, and it's going to be about electronics. This is a perfect workshop if you're getting into electronics or you need a refresher on some of the basic concepts. If you head down to the description, you'll find a link where you can learn more about this workshop, and you'll also find a 50% discount code if you decide to purchase the workshop. There are only 16 seats available, so make sure you go sign up quickly.